Okay, welcome everyone. In this video, we're going to look at the ARM single cycle data path, and we're going to trace one of the data transfer instructions, one of the D-type instructions, okay? And I'm going to show you particularly a store instruction, okay? Now, the load instruction is a little bit different, so keep in mind there are some nuanced differences. You want to always remember, what are these instructions doing? What is the goal of, what is the processor trying to do to support actually processing this? So what I mean, right, is remember here that for the data transfer instructions, right, we have this here, the base address plus the offset defines the address, the memory address. Okay. And because this is a store instruction, we are going to write to this memory address. Okay. If it was a load, we would read from it. Okay, we would read from it. In this register here, we are gonna read from that and write the result in that memory address. Okay, so it kind of looks like this, or if we have our memory, okay, we are going to, in this case, read this address, the stack pointer address, plus 12 for the offset, and we're going to set it equal to register 5. Okay, that's effectively what that's doing. Nothing really new there. Okay. So because we effectively need to get this to work, we are going to have to read two different registers. Okay, if you think about it for a moment, that should make sense that we need to read this register. Okay, but we also need to read this register that contains the base address. Okay, the base address is also read. Okay, so we are going to need to know this, okay, as well as this, okay, because we are going to read from both of those. Okay, so those registers in our register file are really important, okay? And just like all the others from the previous videos, we know that our program counter is going to be set to that because this is the current instruction that we're tracing, the one that we're running, okay? All right, so let's start from there. Let's look at the program counter 10100. Okay, 10100. We know that's the program counter. We know that's the address we're going to read from instruction memory. And we know, just like all the others that we traced, that the default behavior is to increase it by 4, okay, unless we're going to look at a branch, like a branch instruction. Okay, we're gonna add 4 to go to the next instruction, so that at the next clock cycle, okay, as we've seen this before, we will go and we will run the next address. We will run the next address of the next instruction that's in instruction memory. Okay, so we've seen that a bunch of times. Just kind of get that out of the way. Right, we've also seen some of the ways of setting up this. I just actually want to point out before we even do that is that, remember, we're going to read two registers here. Okay, we're going to read two registers, and we don't write to any. Okay, but think about this over here, right? We're reading two registers. We're not writing to any registers. So that tells us a couple things, right? That we need some values for read register 1 and read register 2. It also tells us that we do not need, or we do not care which register would be set to write to. Okay, we do not care, right? The reason for that we don't care is because we aren't going to write to a register. Reg write is going to be 0, indicating, hey, we're not writing to any register. A store does not write to a register. Okay, this instruction that we're running, okay, store instruction, does not write to a register. I think it was register 5. Yes. Okay. All right. So we don't care about this here. We're register writing to, or what the value set there, because we're not actually going to write to anything, write to any register. Okay, we have the opcode up here, just like always. All right, our opcode, 5 ones followed by 5 or 6 zeros, 5 ones followed by 6 zeros. Okay. All right, we're going to read in something here. Okay. And let's take a look at how we figure out how we're reading this second register here. So if we look at the binary here, right, we've got the registers are both in the rightmost bits 0 through 9, effectively. Okay, bits 0 through 9. So 0 through 4 is going to be our register 5, right? And so notice that 0 through 4 down here is actually going to go this direction, right? Register 5, okay, goes this direction here. Okay. It's register 5. This here, register 5, notice it's these last 5 bits, goes here. And the reason for that, as we'll see more in a second, is that we are actually going to take that value and that gets fed into data memory. Okay. Right? We don't, at no point, we're not adding anything to this value here. This is what we're writing into memory. So we actually feed that around right into data memory. So that is going to be value 1011. Okay, 1011. Okay. And the other register that we read is the stack pointer register. Okay, that's register 11100. Okay. Oops, over here, 11100. Okay, and that register has value 1100. 1100. Okay. Now, this 12 is the data transfer address here, these 9 bits. Okay, so in this case, what's going to happen is, let me just kind of edit this a little bit. Okay, this is the 9 bits here is going to get transformed into 32. Okay, these are going to be the 9 bits that represent the data transfer address. Okay, and I'm just making a tiny little change to the diagram because we're dealing with a 32-bit, we're going to stick with a 32-bit registers, okay? So we have these 9 bits that represent the data transfer address, okay, 1100, right, or 12 in base 10, okay? And it becomes the 32-bit version of that over here. I'm not going to write out all 32 bits because that gets crazy. Okay, and that gets fed into this here. Okay. All right, so we look at that. We actually have 12 plus 12, it looks like. Okay, because we have the stack pointer, right? 8 plus 4, 12, plus 12 is the offset, so we have 24. Okay. 24 as our result. Okay, so 16 plus 8 is our 24. Okay, should look like that. And we're going to use this address 24. Address 24 is going to get written to with this value, 1011. Okay. Now, we're getting very close to done. We don't read anything out. Okay, we don't write anything out. Right? Nothing gets written back to the register. Okay, so the write data and write register don't matter. Okay. And to be thorough, let's just kind of trace these control signals too while we're at it. Okay. We know that this very important control signal here. Okay. Oops, I had the wrong color selected, but that's supposed to be... Right, that's the value 1. Okay. The ALU source here, we know that that must also be 1, right? And we can remember, you don't have to memorize this and you don't need to look it up or anything, right? The reason is it has to be that way, right? If you take this offset 12 coming from here must get added to the value of the stack pointer coming from the register file. Okay. We know that the ALU is also performing an add operation. Okay, it's adding this value of the stack pointer plus 12. Okay. We can do some of these, right? We've seen this a number of times. The unconditional branch is 0. It's not an unconditional branch. It's also not a conditional branch. Okay, 0 and 0 is 0. 0 or 0 is 0. Okay, well, at some point, in class, we'll look at a branch operation. We'll see how that can change the value of the program counter. You can probably get a pretty good idea of how that works without even seeing it, but we can certainly run through it. Okay, if we trace this signal here, this is the mem read. We're saying, hey, are we reading from memory? Okay, we are not reading from memory. Okay, we're over here, we're writing to memory. The store writes to memory. So that is a 1 for the store. Okay, we need that control signal to say, hey, we are writing to memory. This signal here, mem to reg, is a don't care. Doesn't matter, right? Because whatever that value selects here is, we don't actually use it. We don't actually write anything back to the register file, so it doesn't make a difference. Okay. All right, that's a quick rundown of the store instruction, a D-type instruction. Okay, keep in mind a load is a little bit different. Okay, because a load writes back to the register file. Okay, it also will read memory, not write to memory. Okay, so because it's writing to a register, the load, right? We need to write to the. We need to have make sure we have part of the bits selecting for a write register, as well as having some data for the data that we're writing to the register. Okay, you should be able to derive what that is, having seen a whole bunch of examples doing other things of what the load is doing that's a little bit different. Okay, and we can certainly run through that in class and answer questions on it. But that we'll do that as wrapping up the videos for the single cycle, now seeing an R-type example, an I-type example, and a D-type example. And I will see you in class, and I will see you in future videos.